Hi, my name is Patrick Vaughn, and today I will be discussing Lab 5, the falling Slinky. I used Newton's second law and Hooke's law to predict the motion of the spring. Newton's second law states that force is equal to mass times acceleration, and also an object will remain at rest or in uniform motion unless acted upon by an external force. I used Hooke's law to find the force of the spring, which is equal to the spring constant times the stretch of the spring. I used data from my observed model to predict the motion of the top and bottom of the Slinky using GlowScript and VPython. The results I wanted to obtain were, does the bottom of the Slinky stay at rest or does it immediately move downwards due to the force of gravity? I found that the bottom of the Slinky oscillates slightly but has a net zero displacement until the entire Slinky reaches the bottom. I also wanted to find out if the predicted model satisfies the energy principle, and I found that no, there is a non-zero change in energy due to an increase in kinetic energy, which is equal to the initial gravitational potential energy at equilibrium. The energy principle states that the change in total system energy is equal to the change in kinetic energy. However, my system is the Slinky and the Earth, so the change in total energy is equal to the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. Here are my initialization conditions for my computational model. I treated the system like 3 masses and 2 Slinkies, a top mass, a middle mass, and a bottom mass, and a top and bottom Slinky. I got the data from my relaxed spring length from the observational model and the mass from an online source. I found that the spring constant is 1.55 kilogram meters a second squared. Ideally, I would predict this motion with upwards of 30 masses to represent a more evenly distributed mass of the Slinky. I set my origin to be mass B, the bottom of the Slinky. I calculated the spring constant, K, using the relaxed spring length and mass values that I found online. I set the force of gravity equal to the force of the spring, which represents the spring in its equilibrium position. I then plugged in my values for mass and S, the stretch of the spring, to find K. Here's my observational model. I set the origin at the bottom of the Slinky and tracked the motion of the top of the Slinky as it is released from rest. As you can see, the bottom of the Slinky oscillates slightly but does not affect the overall motion of the Slinky. Here is the code for my net force and position updates for my predicted model. First, I found the gravitational force on all 3 masses to be negative of the ball's mass times the gravity. I then found the spring force for the top and bottom spring using Hooke's law, which states that the spring's force is equal to the spring constant times the stretch of the spring times its unit vector. Here I set up conditional statements for the 3 stages of my spring's motion. This conditional states that if the length of spring B is equal to or less than its relaxed spring length, that I should run the following code. This is the final stage of the spring's mass. Essentially, the spring has compressed completely and begins falling down at the force of gravity. So I set the net force equal to the force of gravity of the 3 masses, and the ball's velocity is equal to the ball's initial velocity plus the total net force divided by the total mass times delta t. This is my implementation of Newton's second law, using force over mass to find acceleration. My second condition is for when the magnitude of the length of the top spring is equal to or less than the top spring's relaxed length. In this case, the force of the first spring is 0, and the net force of the first 2 masses is equal to the force of gravity of the top mass plus the force of gravity of the bottom mass plus the force of the bottom spring. The net force on the bottom mass is equal to the force of gravity of the bottom mass plus the force of the spring B. I then updated each mass's velocity. The first 2 masses are equal to the first mass's velocity plus the total net force on those 2 masses divided by the total mass of the 2 masses times the change in time. This is again my implementation of Newton's second law. The bottom mass's velocity is equal to the initial velocity plus the net force of the bottom mass divided by mass. The velocity for ball B is equal to its initial velocity plus its net force over its mass times delta t. Here's my third condition. This is considered the first stage of motion of the spring. Essentially, I set net force for each of the masses equal to the force of gravity plus the force of the spring. However, for the first mass, it's equal to its force of gravity plus the force of the top spring. For the middle mass, it's equal to the force of gravity plus the force of spring B minus the force of the top spring. And for the final mass, its net force is equal to the force of gravity minus the force of the bottom spring. Here I update the position for all three masses regardless of the conditions that they went through before. So for ball T, its position is equal to its initial position plus its velocity times the change in time. Here I use Hooke's law to update the top and bottom springs. Here I use the energy principle to calculate the final kinetic, gravitational potential, and spring potential energies of the system. Here's what my computational model looks like for my predicted motion of the falling Slinky. As you can see, the two Slinkies that I used to model this motion have different stretch. Here I compared the position of the bottom of the Slinky versus time for my predicted and observed models. As you can see, in the beginning, both models oscillate at a slightly different rate. However, once they reach time 0.35 seconds, they start to drop. This is because the Slinky has finally caught up and begins to fall at the force of gravity. Here is the comparison of the Y position of the top of the Slinky versus time for my predicted and observed models. As you can see, my predicted model has a smoother descent than my observed model does. This is mainly because I used more data points in my predicted model than in my observed model. However, they both fall at, although their positions are relatively close, my predicted model fell further because of, again, dissipative forces that were not taken into account. What does it mean? Is the energy principle satisfied? The change in total system energy is not equal to zero. No, the change in total system energy is not equal to zero, as you can see by the two spikes in total energy on the change in energy versus time graph. Because my computational model has the masses set up in chunks instead of spread out across the entire length of the Slinky as it would be in my observational model, once my middle and bottom masses begin to fall, they begin to ramp up in kinetic energy, which does not match up with the gravitational potential energy that they had initially. That's all. Thanks for watching.